So I don't introduce Andrea a second time. Everybody knows him now. And please.
Yeah. So yeah, thank you for the ones who are still attending this series of lectures, and again, thanks for the kind invitation. So yeah, today is a second lecture. So let me start with the recalling what we did yesterday. Okay, so let me just move. Okay, yeah. So yesterday we have seen the definition of the CDKN condition, so which is a synthetic way of saying that a metric measure space has Ricci curvature bounded below by K and dimension bounded above by N. So K is a real parameter, and N plays the role of upper bound on the dimension, and it is also a real parameter ranging from 1 to plus infinity. So we have seen that this is the notion of Lott-Villani. And so a metric measure space is a CDKN if the n entropy, so for n finite is the Riemannian entropy, for n infinite is the Boltzmann entropy, is K convex along geodesics in the Weierstrass space. This is precise when n is infinity. When n is finite, one has to be a bit more careful in writing down the precise notion of convexity. But just to keep in mind, let me mention the two easy cases to write down, which are n equal to infinity, which means the CDK infinity condition, and this K convexity means that for any couple of probability measures, so mu0 and mu1 are probability measures with finite second moment, there exists a W2 basic, mu t, joining mu0 to mu1, such that for every time t, it holds that the entropy, the Shannon entropy, at mu t is bounded above by 1 minus t entropy at the initial point, plus t entropy at the final point, minus this kind of modulus of convexity. And when k is equal to 0, this is exactly the standard convexity of functions. When in the finite dimensional case, as I was saying, when k is not 0, then you have to be a bit more careful, and the convexity uses the so-called distortion coefficients, which for k positive involves the trigonometric function, so sine, cosine, and with k negative involve the hyperbolic trigonometric function, so hyperbolic sine and hyperbolic cosine. But for k equal to 0, it reduces to standard convexity. So let me state it. So the CD is 0 n condition means that for any couple of probability measures with finite second moment, there exists a W2 geodesic joining them, such that for any intermediate time, it holds that the standard convexity condition holds along the curve. Okay, so this is what we did yesterday. We also did the stability of CD. So let me recall the theorem. So fix some k in R and some n in 1 infinity. Let's consider a sequence of pointed metric measure spaces, xn, dn, mn, with the reference point x bar n, and assume that they satisfy the CDKN condition for such fixed parameters, and they are converging to a limit space, x infinity, in the pointed measure Gromov-Hausdorff sense, or more generally, as we've seen yesterday, this pointed measure Gromov convergence. Then the limit space, x infinity, is CDKN as well. And this is true for n finite or for n infinite. And we saw yesterday that for n infinite, it is more natural to consider this pointed measure Gromov convergence, while for n finite, the pointed measure Gromov convergence is very natural. Okay. Now, from the stability of CDKN and from the fact that smooth manifolds, say for a smooth Riemannian manifold, the Ricci is bounded below by K and dimension is bounded above by N, if and only if it is a CDKN space, it follows that any limit of any pointed measure Gromov limit of a sequence of Riemannian manifolds with Ricci bounded below by K and dimension bounded above by N is a CDKN space. in other words, if you consider Ricci limits of dimension at most n and Ricci bounded below by k, all of these Ricci limits are contained in the class of CDKN spaces. Okay, so this was a recalling of what we did yesterday. So the plan of the talk of today is to first introduce the so-called Riemannian CDK infinity condition, then then discuss the relation between the RCDK infinity condition and gradient flows, and then move to the five-dimensional theory. So I will discuss the RCDKN and RCD star Kn. And we're going to see that these gradient flows play a really important role in the theory, because they will permit to prove very important functional inequalities like the Bochner inequality. Okay, so let's get started with the RCD K infinity spaces.
There's a question in the chat.
Yeah. Chat. Yeah. Yeah, we know that Ricci bigger than kg can be interpreted as K convexity for a metric space. So how do we translate Ricci equal to G in the case of metric space? Yeah, this is a very good question. So you can do it. Okay, so what I will discuss in this series of lecture is Ricci lower bound. And Ricci lower bound, as we just seen, let me just go back to the slides that we have all in front of us, is convexity of the entropy for any two probability measures, which are actually want to be, if one is precise, mu0 and mu1 are absolutely continuous with compact support yeah. In any case, you can take any two probability measures which are very far away, and you ask the convexity along this along a geodesic which is connecting these two probability measures. So they could be very far away. If you want to speak about Ricci equal to kg, then there are various ways. The way the optimal transport was proposed by Sturm. And the idea is that you have a lower bound, and then you want to characterize the optimal transport also an upper bound on the Ricci. How to do that? So the lower bound, roughly the lower bound is convexity of the entropy. The upper bound, you want to say it is concavity of the entropy. However, it is not just as simple as that, because while the lower bound, while for the lower bound you have convexity of the entropy along any Wastein geodesic, if you want to characterize the upper bound, you have to consider geodesics. So you have to consider probability measures which are very concentrated near points and which are also very close. So you have to think of mu0 and mu1 as perturbation of Dirac deltas of 2 points which are very close. And moreover, you cannot ask it for any, then you cannot. Okay, so the idea is to ask for a concavity of the entropy along a geodesic of probability measures connecting these two measures which are very concentrated and very close. But you cannot ask it for any geodesic. You have to ask just it for a geodesic which is shoot by a Kantorovich potential with very small Hessian. So it needs a little bit more of technicality, and it is more subtle. But you can do it. So the idea that for Ricci equal, you have the lower bound, and then you want to characterize the upper bound on the Ricci. The upper bound, I was saying, is concavity of the entropy, but just along very, very special measures. This is the way the optimal transport. And then there's also a way of characterizing both lower and upper bounds on the Ricci using going to understand the path spaces. And this is the approach of Naber, which was then say further investigated by Naber and Hasselhofer. And yeah, so there is more than one approach.
Thank you for the answer. It's very clear.
Yeah, very good. Okay, so if there is no more question, I will continue. All right. Stability. Okay, so I was saying that we are moving to the RCD K-infinity spaces. Okay. So why we would like to introduce some new spaces, since the CD spaces are so natural and they are stable and one can prove so many inequalities. Well, let me introduce the topic. So from the stability of the CDKN class, we have that any limit of a sequence of Riemannian manifold which is going below and the dimension bounded above is a CDKN space. And so, as we were saying in the beginning of this lecture, the CDKN spaces contain Ricci limits of manifold of dimension at most n. Okay, but the CDKN spaces contain also Finzer manifold. So one can see that a Finzer manifold with Ricci-Colding bounding from below. So you can also make a notion of Ricci-Colding bounding from below in the Finzer setting. They are CDKN. So if you have an n-dimensional Finzer manifold with Ricci-Colding below by k, then it is a CDKN space. Just to fix the ideas with something very concrete, if we consider Rn with any norm, so this is any norm, and with the Lebesgue measure, the n-dimensional Lebesgue measure, then this is a CD0n space. Okay, so here you can put any norm. If you have the Euclidean norm, you have standard Rn, but here you can put any norm, even the L-infinity norm, which is quite pathological from the point of view of geodesics. But as a fact, which was proved by Cheeger and Colding, if a smooth Finzer manifold appear as a Ricci limit, then actually the manifold is a Riemannian. So purely Finzer structures never appear as Ricci limit spaces. So you never see Finzer structures as Ricci limits. And so, in some sense, the class of CDKN spaces is too large because it contains too many objects if you want to study a synthetic class which contains manifold and Ricci limits, but does not contain too much more. In addition to that, because maybe you can say, well, it contains more objects, but I can prove theorems and I'm happy enough, and this would not cause too many troubles. But more importantly, some fundamental theorems in comparison geometry of Riemannian manifolds are not true in the larger Finzer category. Let me, for instance, mention the famous and celebrated and super important splitting theorem by Cheeger-Gromov. This fails in the Finzer category. So the splitting theorem says that if you have a Riemannian manifold with the Ricci non-negative in which contains an isometric immersion of a line of R, then it isometrically splits R. But for instance, if you consider R2 with say any norm, so with the L-infinity norm, this is CD02. It contains a line, so for instance, the x-axis is a line, but it does not split isometrically, just because it is not. So you don't have the Pythagoras theorem because you don't have the Euclidean norm here. Okay, so if you want to, so the point is that you enlarge your space of Ricci limits with all the CDKN. But then you cannot expect to be able to prove some fundamental theorem in the class of CDKN because you have too many objects. Okay, so we wish to reinforce the CDKN condition in order to isolate those CDKN spaces which are kind of Riemannian. Okay, so in other words, we would like to rule out Finzer structures, but in a sufficiently weak way to still get a stable notion under pointed measure Gromov-Hausdorff convergence. Because if you restrict your space too much, for instance, you say, well, I just take a smooth manifolds or a smooth manifold plus the Ricci limits, if you restrict your class too much, then your class may not be stable under pointed Mondino-Hausdorff convergence. And remember that we would like to play the game that we want to have a synthetic notion. So we don't want to appeal on smooth structures and just limits of smooth structures. We want to have a kind of intrinsic way of saying that a metric space has Ricci bounded below YK. Okay, so this is the next goal. And so the problem is how to isolate the Riemannian structures among the possibly Finsler ones. So the Riemannian structure is the one where the norm is a scalar product, at least in the smooth case. And when does the norm is a scalar product? Well, it is when it satisfies the parallelogram identity. Okay, so this is at the level of smooth spaces. Now, if we are on a non-smooth space, we don't have really a norm, and we don't have really a tangent space with a norm. So how to see the Riemannian or Finsler behavior? Well, we can work with functions. So on a metric space, we can define function, we can define a two function, we can define a Lipschitz function, etc. And the idea is that is to look at the Dirichlet energy of functions. So in a metric setting, the Dirichlet energy is not called Dirichlet because Dirichlet forms are something very special in metric geometry, but it was studied by Cheeger, the natural extension of Dirichlet energy in a metric setting. And how to define it? So notice that defining the Dirichlet energy is not super clear in a metric setting because the Dirichlet energy is the L2 norm squared of the gradient of a function. The gradient of a function is element of the tangent space, and if the tangent space is not well defined, is not linear, etc., it is not immediate to define what is the gradient of a function. But at least one has a very classically well-defined notion of modulus of the gradient, which is called minimal Wickham gradient. And in the Cheeger energy, it only appears the modulus of the gradient. So the Cheeger energy, the Dirichlet energy is the L2 norm squared of the modulus of the gradient of a function. Okay, so you can define the Cheeger energy using the Wickham gradient, which is kind of the modulus of the gradient. If you prefer not to take this as a black box, then you can define it using the slope, the local Lipschitz constant of a function in this way. So consider you want to define the Cheeger energy of some function f. So what you do, you consider all the possible ways that you can approximate your function f with locally Lipschitz functions, and you want to approximate in the L2 topology. So you consider all the possible sequences UN which are converging in L2 to your function f. For any local Lipschitz function, you consider the local Lipschitz constant of this function u. You square it and you integrate it over x. This is well defined. It would be plus infinity if Lipsch u is not in L2, but in any case it is well defined. And then you take the limit over all these possible approximations. So this is called the L2 lower semi-continuous relaxation of this functional here. Okay, but at least you have a well-defined notion of Dirichlet energy, which in the metric setting takes the name of Cheeger, because was the first one to introduce it. Okay, and now the crucial observation is that on a Finsler manifold M, the Cheeger energy is quadratic, meaning that the parallelogram identity holds, if and only if the manifold M is actually Riemannian. Okay, so a metric mesospace where the Cheeger energy is quadratic is said infinitesimally Hilbertian, and it is what we have in mind as a kind of non-smooth, kind of Riemannian space. Okay, and now the idea, since this rules out thinner geometries, the idea is to reinforce the CD condition by asking that the Cheeger energy is quadratic. And so the Ambrosio-Gigli, and based on this idea, Ambrosio-Gigli and Savarè proposed to reinforce the CD K-infinity condition with this notion of infinitesimal libertianity, and they called this class of spaces RCD K-infinity. So an RCD K-infinity space is a multi-major space, which is CD K-infinity, and it is infinitesimal Hilbertian. So it is CD K-infinity, and the Cheeger energy is a quadratic form. Okay, so this was the idea in Ambrosio-Gigli and Savarè. Let me just mention it to be precise. In Ambrosio-Gigli and Savarè, the axiomatization was a bit different. So instead of CD K-infinity, it was asked a kind of stronger notion of CD K-infinity, and they were working with a reference measure which was of probability. And then the axiomatization was simplified in this way, so CD K-infinity plus infinitesimal Hilbertianity, and extended to any sigma finite measure M in subsequent work by Ambrosio-Gigli, myself, and Rayala. Okay, but the key idea of using the Cheeger energy was in the original work of Ambrosio-Gigli and Savarè. Okay. Now we ruled out since there are geometries. We are quite happy, but remember that our goal was to detect a stable condition. So now the fundamental question is the RCD K-infinity condition stable under pointed measure Gromov convergence? Okay, and notice that the stability here is more subtle, because say the stability of the CD K-infinity condition is morally due by the fact that convexity is stable under a zero-order convergence. Indeed, as we have seen yesterday more in detail in the lecture by Cristina Sormani, one can see the measurement of convergence as a kind of weaker zero-order convergence of the distance functions. So we have a zero-order convergence which is weaker than, say, uniform convergence of the distance functions. And the CD K-infinity condition is a convexity condition on the entropy. Okay, and morally, we know from first year of university that convexity is preserved by zero-order convergence. Indeed, if you have a sequence of functions from 0, 1 to R, which are convex, and they converge pointwise to a limit function, then the limit function is going to be convex as well. Okay, so morally, convexity, so we know that convexity is preserved by zero-order convergence. Of course, here is much more subtle because, say, as you have seen, you have much more things going into the play, but say, the moral is that. Now, the RCD K-infinity, yeah. A question?
From the chat.
Yeah, let's see. Is the CDKN obtained as limit of Riemannian? I will go, Andre. Is the CDKN obtained as limit of Riemannian plus Finsler with curvature bounds? No, I don't think so. No, the CDKN is obtained as limit of Riemannian plus Finsler with curvature bounds. I don't think so. But I don't have a... I will discuss this for the RCD. For the CD, I think that the same example may work, but the proof doesn't. So I will address how bigger is RCD with respect to the Ricci limits in the second part of this seminar. The answer to your question, I think the answer is no, but I don't have a definite answer. I have a feeling more than a proof. Okay. But that's a good question, and I think it is something that say a postdoc, someone interested could go for it, and it's an interesting question. Okay, so I was saying about stability of RCD. Okay, so we're saying that the stability of CD is kind of natural because convexity passes the limit under zero order convergence. But what about RCD? So RCD is convexity of the entropy plus a first order condition. So this quadraticity of the Cheeger energy is something which involves gradients of functions. So it involves something at first order. We have derivatives. So we have first order objects. And why something of first order should pass into a limit under a zero order convergence? So in general, you simply have no hope. So if you ask some first order condition on function from R to R, and these functions are converging pointwise, then there's no reason why this first order condition should pass the limit. And in general, it's completely false. You have no hope for doing it. But what saves us? So why you have some hope here is that because you have this zero order convergence, or this measurement of convergence is coupled with a uniform second order bound, which is the convexity of the entropy, which is the lower bound on the Ricci, which is a second order object. So having a zero order convergence coupled with a second order bound gives you some hope to prove some stability for first order objects by interpolation. Okay, so that's not the proof, and that's very far from the proof, but it is kind of a moral why you can expect the RCD condition to have some hope to be stable under pointed measurement of convergence. Okay, so now let's address the stability of RCD K infinity a bit more in detail. So the RCD condition is in terms of the Cheeger energy. So the Cheeger energy, by definition, is lower semi-continuous on L2, just because it's the lower semi-continuous relaxation of the Lipschitz constant. And one can show quite easily that it is convex. So the Cheeger energy is, as a functional defined on L2, is convex and lower semi-continuous. And so one can apply the classical theory of gradient flows, for instance, by Brezis, and show that it admits a unique gradient flow that we're going to call the heat flow. Okay. Now, if we have a sequence xn of spaces which are converging in pointed measure of sense to a limit space x infinity, then one can say that there is also a natural way to define convergence of a sequence of functions fn defined on xn to a limit function f infinity defined in x infinity, and one can speak of weak convergence, strong convergence in L2, etc. The basic idea is that by definition of pointed measurement of convergence, we are embedding all this xn and this x infinity in an ambient space, and with some care, this is not so easy, but one can use this ambient space to have an L2 convergence there. Okay. Now, once one has this notion of convergence, an important result for the stability of the RCD condition is to study the stability of heat flows. So one can prove that if xn is converging to x infinity in the pointed measurement of sense, and all these xn's are CD K infinity spaces. Okay, so this is the framework. Now consider now for each n, consider an initial datum for the heat flow, which is in L2. So Fn is in L2 of xn. And assume that these initial data are converging strongly in L2 to a limit function f infinity in L2 of the limit space x infinity. Okay, so you have pointed measure of convergence of xn to x infinity. All the xn are CDK infinity spaces, and then for every n you have initial data in L2 which are converging strongly in L2 to an initial datum f infinity of the limit space. Okay, then the theorem says that also the heat flows are converging strongly in L2. So the evolutions of this Fn via the heat flow, so this heat flow at time t, is converging to the evolution at time t of the limit function f infinity. And if you had the strong convergence of the initial data, you also have a strong convergence of the heat flows. So one can see this as a stability result for heat flows. So the proof is a bit complex. So the proof is a bit technical. I just wish to mention the few, say, the main steps of the proof. So the key idea of the proof is to use an identification result between heat flow in this framework that I discussed, or the heat flow as a gradient flow of the Cheeger energy in L2, and the fact that such heat flow corresponds to the gradient flow of the Boltzmann-Shannon entropy in the vast space that I'm going to discuss actually later, but you can keep it. So you have two equivalent formulations of the heat flow. One is gradient flow in L2 of the Cheeger energy, and the other one, which is equivalent, is gradient flow of the Shannon-Boltzmann entropy in P2. And these two descriptions are equivalent. And this was proved in the smooth setting by Lott-Villani, and in the RCD setting, in the 3D setting by Ambrosio-Gigli and Savarè. Okay, once you have this identification, you use that these Cheeger energies have a good convergence under the underlying convergence of the spaces. So if the xn's are converging in pointed measure of Hausdorff sense, then the Cheeger energies converge in the so-called Mosso convergence, which is an adapted way of the gamma convergence that I discussed in the lecture of yesterday. Okay. Once you have this convergence of the Cheeger energies, you have convergence of the resolvent maps that say I don't want to enter into much into details, but basically the idea is that you are discretizing in time the heat flow, and each time discretization corresponds to a resolvent map. Now, once you have the convergence of the resolvent maps, you approximate the heat flow by discretizing in time, so by iterating resolvent maps, and you conclude. Okay, so the proof is actually quite complicated, but I just wanted to give a few key ideas for people who are interested. Okay, so this is the stability of heat flows in L2. And now how to link it with the stability of the RCD K infinity condition. So we have seen that by definition, your space is RCD K infinity if it is CDK infinity and the Cheeger energy is quadratic form. Now, a functional is quadratic if and only if its gradient flow is linear. This is an easy exercise. And so XDM is infinitesimal Hilbertian if and only if the gradient flow of the Cheeger energy, which is the heat flow, is linear as a map from L2 to L2 for every positive time. So we can use the stability of heat flows in order to pass into the limit the linearity of the heat flow and then the infinitesimal Hilbertianity. And indeed, this was what we did in the paper with Gigli and Savarè to prove that the RCD K infinity condition is stable. The fact that RCD K infinity condition is stable was proved also in the previous work by Ambrosio-Gigli and Savarè, but under more stringent assumptions on the spaces. So they were assuming that the measures M were absolutely were probability measures, and if I remember well, also the spaces are compact or bounded. And they used a different argument using gradient flows in a different way. They were using the EVA formulation of the RCD condition. But let me know. I will discuss that in the next slide. So now let's just fix the notation, the point of view of heat flows. Okay, so what is the statement? The statement is the following. Consider a sequence of metric measure spaces, Xn, which satisfy the RCD K infinity condition for a given K, and they are converging in pointed measure Gromov sense to a limit space X infinity. Okay, then the limit space X infinity is RCD K infinity as well. Okay, now, the proof is actually quite easy once we have the previous stability result of the heat flow. Indeed, we already know by what we discussed yesterday and I recall this morning that the CD K infinity condition is stable. So my Xn are RCD K infinity, so they are CD K infinity and infinitesimally Hilbertian. So the CD condition passes the limit, so X infinity is a CD K infinity space by what we know. Now, what we just need, so what is remaining to show is that X infinity is also infinitesimally Hilbertian. But from this fact, we have that X infinity is infinitesimally Hilbertian if and only if the heat flow is linear as a map from L2 to L2 for every positive time. But we know that Xn are infinitesimally Hilbertian, so the heat flow is linear for every n as a map from L2 to L2 for every positive time. Now, from the previous theorem, the heat flow is passing to the limit, and then this implies that also the limit heat flow is linear, and so also the limit space is RCD K infinity. Okay, so this is a brief sketch of the stability of the RCD K infinity. So this idea of the proof is not so far from the real proof. So it is really just a consequence of the stability of the heat flows, while the stability of heat flows is actually more tricky. Okay, now I would like to discuss in a couple of slides an alternative way of defining RCD K infinity spaces using gradient flows, because this will be useful later when we talk about the Bochner inequality. Okay. So here I'm opening a parenthesis about gradient flows in metric spaces. So consider a geodesic space Y with distance dy. Geodesic means that any 2 points can be joined by a Leninizing geodesic. And later we're going to take as Y the space of probability measures over a space X with endowed with W2 vastness distance. Okay. Now, but for the moment, it is just a metric space. It is just a geodesic metric space. Now, by definition, we say that a functional E from Y to R, and possibly taking the value plus infinity, is said to be K-convex, with K is a given real parameter, if for any 2 points Y0 and Y1 in Y, there exists a constant speed geodesic gamma from 0, 1 to Y, such that the initial point of the geodesic is Y0, and the final point of the geodesic is Y1. So we are given 2 points Y0 and Y1. We want that there exists a constant speed geodesic joining these 2 points. Okay, and we ask that this convexity condition holds along this geodesic. So we ask that for K equal to 0, we have the standard notion of convexity, and for K different than 0, we have this kind of modus of convexity, and this should ring a bell, right? Because this is exactly what we asked for the entropy along Wasserstein geodesics. Okay, but for the moment we are on in an abstract setting with any function. Now a key observation. Consider as metric space Rn, so we are back home with our old friend Rn, and we consider a smooth k-convex function. Okay. Now, if f is a k-convex function on Rn, then we want to characterize the minus the gradient at some point x. And it turns out that a vector v is minus the gradient of f at the point x, if and only if this inequality holds. So let's read it together. What I'm saying is that v scalar product, the difference between x and y, plus this k modulus of convexity, plus f of x is less or equal than f of y. Now, in order to get the feeling, that let's just take k equal to 0, just to simplify our life, so that our function f is convex. So what we are saying is that f of y is bigger or equal than f of x. Then here we have a minus, so let's say plus grad f y minus x. So this is basically saying that f of y is bigger than the first order expansion of f at x if we choose v equal to grad f. If you know a little bit of convex function, this is nothing but saying that this v is in the subdifferential of the function f. And if the function is smooth, then you just one element in the subdifferential, which is the gradient. Okay, so this is an exercise. So if you take k equal to 0, it is really just an exercise of analysis to check this. Okay, and that's it. Any question about that? No? Okay. So now we can use this characterization of minus the gradient to characterize a gradient flow. Okay. So what is a gradient flow of f is a curve such that at every time the time derivative is minus the gradient of f. Okay. So how we make show up the time derivative? Well, we can just consider the time derivative of the distance between xt and some given point y. If you differentiate it in t, you will get exactly this guy here. Okay, so using this exercise, we can say that a curve xt is a gradient flow of the smooth and k-convex function f, if and only if for every y in Rn this inequality holds. So the time derivative of the distance between xt and y square over 2 plus k over 2 xt minus y plus f of xt is less or equal than f of y. Okay, and this is an exercise that you can give in an exam in analysis 2. It's second year. Okay, but now this is very powerful if you abstract it to a metric setting, and you say that by definition you have an EVI k gradient flow if that previous inequality is satisfied. So let me say it. So you fix a geodesic space y, and you fix E a lower semi-continuous functional, then a locally absolutely continuous curve yt, such that at every time the functional E is finite along y, so this yt is in the domain of the functional E. You say that it is an EVIK gradient flow of E if the previous inequality is satisfied. So the time derivative of the distance squared from yt to z over t plus this k over 2 distance squared from yt to z plus the value of the functional at yt minus the value of the functional at z is, we have this inequality for almost everything. Okay. Now a general remark, which is not completely immediate, but it is also not too hard, is that the existence of an EVIK flow. Is there some question?
Yes. What does it mean, a locally absolutely continuous curve?
Yeah, it is. So it is with values in a metric space Y. So in Y you have you can define so you have the so-called metric speed of a curve, which means that you are taking so the formula is that you have the distance of
rectifiable, so that the speed is locally is absolutely continuous with respect to.
That's correct. It means that the speed, the metric speed, is locally in L1. That's correct.
Thank you.
Yeah. Okay. So the the existence of an EVIK flow actually depends on both the space and the functional E. So it is strictly related to the fact that the functional E is K-convex, and the fact that your space is infinitesimally Hilbertian. For instance, if you take a convex function on Rn, and you ask if it admits an EVIK flow, well, it admits it only if in Rn you choose the scalar product, the Euclidean scalar product. But if you instead choose a different norm, you don't have the EVIK property. So you are given. So this EVIK condition is really something strong, and is encapsulating both the geometry of your space and the geometry of and the convexity of your functional E. And in general, the existence of an EVIK flow is not true, and is something remarkable if you have it. And once you prove the existence of an EVIK flow, then you have a lot of nice properties of the flow itself. One has nice contractivity properties and regularizing properties of the flow, which are not immediate from the definition, but they are true. And say a monograph which is dedicated to this is the book by Ambrosio-Gigli and Savarè in the ETH lecture notes, if you want to see more about that. Okay. And now, how is it related to the RCD K-infinity condition? Well, one can prove that a metric measure space XDM is RCD K-infinity if and only if for every probability measure mu in the finite cycle moment with support containing the support of the measure m, there exists an EVIK flow of the both functional entropy starting from mu and evolving in W2. So we are taking the EVIK flow of which functional of the both functional entropy and in which space, in the space of probability measures with finite cycle moment endowed with the W2 Base-time distance. And this was proved again in the case of M probability measure by Ambrosio-Gigli and Savarè, and then was extended to the general case by Ambrosio-Gigli, myself, and Rayala. Okay, the proof is not immediate, and I would like to skip it because I want to do something else in the finite dimensional theory. But let me just mention that this EVIK formulation is useful for proving the stability of RCD K-infinity, and this was indeed the point of view of Ambrosio-Gigli and Savarè in their initial paper. And this EVIK formulation is also useful to prove that the RCD K-infinity condition is equivalent to the Bochner inequality for n equal to infinity. And this was done in this paper by Ambrosio-Gigli and Savarè. And I will actually, so one implication was in this paper, and then the equivalence with Bochner inequality in the n infinity condition was in a subsequent paper 1 year later. And I will discuss it. I will discuss the Bochner inequality in the finite dimensional case in the second part of this lecture. So now the next chapter of the lecture is going to be the finite-dimensional theory, so RCDKN. So I think it's a good moment to have a 1 minute break, and if you have some questions, I will be happy to discuss.
There's a question in the chat. What does EVI stand for?
EVI.
Okay.
EVI.
What does EVI stand for? It stands for evolution variational inequality. I know it is more clarifying, but yeah, because it is, so it is right. So it's because it is a variational inequality in the sense that you have inequality which takes care of, say, which is of variational kind, and is evolution because you are evolving in time. But yeah, I didn't give this name. Okay. And K is the parameter K which enters in the definition in definition of EVI. Okay, so if there is no more question, let's move to the finite-dimensional theory. Okay, the finite-dimensional theory is this RCD star Kn and RCD Kn spaces. So I will try to make a bit of order between this star and non-star that bugged for a few times. So what is this star condition? So this star condition is, so we last so in the last lecture we have seen that we have seen the CDKN condition. But then in the literature appeared this CD star Kn condition. What is that? So it is it is called reduced curvature dimension condition, and it was introduced by Bacher and Sturm in 2010. So quite in the quite some time ago. And why they introduced the CD star condition? Well, this is a modification of the CDKN condition, which asks a priori weaker convexity condition on the Riemannian entropy. So what is always true is that the CDKN condition always implies CD star Kn. So CD star is always weaker than CDKN. But knowing that your space satisfies the CD star Kn condition will tell you that it satisfies the CDKN condition with a possibly worse lower bound on the Ricci. So CD star Kn implies CD for a lower bound K star, which is slightly worse than your previous lower bound. Why Bacher and Sturm introduced the CD star Kn condition? Well, because an important problem of this curvature condition that I have not addressed so far is the so-called local to global. So a feature that one would like of the curvature condition is that one would like to know that if one checks locally that locally that your space is as the curvature that you want, and you check it locally, but you can cover with the local neighborhoods all your space, then globally your space will satisfy your curvature property. So more precisely, locally, I mean at every point as a neighborhood which satisfies this condition. Okay, but for the CDKN condition, it is simply not true. So if you don't ask, if you ask no assumption on your space, there are counterexamples. There's a paper by Rayala in Annali Scuola Normale that give an example of a space which satisfies CDKN locally, but globally it does not satisfy CDKN. Okay, so the CDKN condition does not globalize without any further assumption. And this is a bit kind of surprising because when you are on a smooth manifold, the Ricci is something pointwise define that it's enough to control that the Ricci is bounded below in every point, where that it is Ricci bounded below everywhere. Here it is more tricky because if you remember the definition of CDKN, your two measures can be very far away. So you're taking mu0 and mu1, which can be very distant, and you're asking about the existence of a geodesic which is connecting the two, which is convex, such that the entropy is convex. Now, knowing that small neighborhoods admit convex geodesics for measures which are supported in this small neighborhood is not helping you so much a priori. And so here is the difficulty to showing the local to global property. So this is just to motivating the local to global problem and to tell you why the CD star condition was introduced. So what Bakker and Sturm proved is that if your space X is non-branching, meaning that geodesic do not branch, then the CD star condition satisfies the local to global property. So the CD star condition holds globally if and only if CD star holds locally, and this is equivalent to us that the CD condition, so the stronger one, holds locally for every k prime less than k. So this k minus means for every k prime less than k. And moreover, it satisfied also some nice condition like tensorization. So if you have the product of non-negative Ricci curved space, the product is still non-negative Ricci curved. And the nice thing is that this CD star condition has the same geometric consequences of CDKN, so Bishop-Gromov, Bonnet-Myers, Lichtner-Ovitz, but linked to this fact of this say worse lower bound, sometimes they have slightly worse constants if you don't assume anything more on the space. Then actually, as a byproduct of something that we will see in the last lecture, which is the localization method, actually, if you assume CD star plus essentially non-branching, then you get all these Bishop-Gromov, Bonnet-Myers, and Lichtner-Ovitz, and say all the inequalities that you can think of with sharp constants also in the CDKN, in the CD star KN framework. But we're going to discuss it in the very last lecture. Okay, so this is CD star. And now, what about now? We have done you can imagine where I'm going. So we said that when we want to rule out finite geometries, we add the infinitesimal libertianity. So one introduces the RCD K infinity condition as CDK infinity plus infinitesimal libertianity, and it is not surprising that if one considers the finite dimensional setting, one adds the infinitesimal libertianity to the CD Kn or CD star Kn condition, and one obtains this RCD star Kn, which is CD star Kn plus infinitesimally Hilbertian, or RCD star Kn, which is CD Kn plus infinitesimally Hilbertian. Okay? And a key property, again, is that such a condition is stable under pointed measurement of the convergence, and one can prove the proof is exactly the same as the one that we discussed for the RCD K infinity. So that, let me just say the statement, so that if you have a sequence of spaces which are RC star Kn, which are converging in pointed measurement of sense to a limit space, then the limit space is RCD star Kn as well. If the sequence was RCD Kn, then the limit is RCD Kn as well. Okay? So as a consequence, we have that all the pointed measurement limits of sequences of Riemann manifolds with Ricci bounded below by K and dimension bounded above by N is an RCD Kn space, and actually an RCD star Kn space, because it is larger. And so we have this inclusion. So we have that all the Ricci limits of n-dimensional manifolds are RCD Kn. all the RCD-Kn are RCD star Kn, and all the RCD star Kn are RCD K infinity for every n and for every k. Okay? Now, a basic question that one can ask was something that was raised, a kind of variant of this question was raised in the chat, is are these inclusions strict or not? So what are these inclusions? Are some inclusion actually trivial? Okay, so let me start by the easiest one, which is RCD K infinity strictly contains RCD star Kn for every finite n, and the example is a Gaussian space. So if you consider the Gaussian space, so Rn with the Gaussian measure gamma n, then this is an example of RCD 1 infinity, but it is not RCD star 1 infinity 1n for any finite n. You can see it very easily because RCD star 1n implies that the space is compact by Bonne-Meyer's diameter bound, but the space is not compact. Actually, it is even stronger. So, this inclusion is even stronger in the sense that it is even strict if you take any lower bound K prime. Okay, so this Gaussian space is RCD 1 infinity, but it is not RCD Kn for any choice of K and for any choice of finite n. This is because RCD star Kn implies a local doubling property which fails in the Gaussian space. Okay, so one inclusion here is strict in a very strong sense. What about the second inclusion? What about the inclusion of RCD star and RCD? So in a very deep paper, this is a result of a very deep paper by Cavalletti and Millman that has just been published in Invenciones this year. They proved that in case the reference measure M is finite, then RCD star Kn is completely equivalent to RCD Kn. Okay, so these two notions are equivalent, at least in the case of finite measure. So actually, there's no reason to expect that this equivalence fails for a measure which is for a general measure, for a sigma finite measure, but the adaptation of proof is non-trivial. So it would be, say, if you want to give a technically challenging, but very likely to be true problem to your PhD student or your postdoc, this is a good thing, and you would do a favor to the community because it is something that it would be useful to be added to the literature. But I don't know if you're doing the favor to your student because you will have to work quite hard. Okay, so so this is one implication. So this is an equivalence. And what about this other implication? So what about the inclusion RCD with Ricci limits? So actually, also here the inclusion is strict in the sense that the RCD Kn, the class of RCD Kn spaces, strictly contains pointed measure factor limits of Riemannian manifolds with Ricci bounded below by K and dimension bounded above by n. Let me give you an explicit example. So consider the cone over RP2. So the cone over RP2 is an RCD 0,3 space. So this is because RP2 is an RCD 1,2 space. So it has a Ricci bounded below by 1 and dimension at most 2. And a cone of an RCD 1,2 space is an RCD 0,3 space. And this was, for instance, proved in a paper by Ketterer, who studied cones over spaces. You can also see that the cone over RP2 is RCD 0,3 by seeing it as a quotient, and then applying another paper by Garcia, Kell, Sousa, and myself, which gives the same thing that the cone over RP2 is RCD 0,3. Okay. All right. However, this RCD 0,3 space cannot be a pointed measure factor limit of Riemannian manifolds with Ricci bounded below by 0 and dimension is bounded above by 3. So why this cannot be? Why you cannot achieve it as a Ricci limit? Well, this is quite subtle, and this involves a recent work by Simon and Simon Topping studying the non-collapsed three-dimensional Ricci limits using Ricci flow. So what they proved is that any non-collapsed three-dimensional Ricci limit is a topological manifold. So, and how they proved it? So the basic idea of their work is that they start from a sequence of smooth manifolds which are converging in of three-dimensional smooth Riemann manifold with the Ricci below, which are converging to a limit space. They want to get some better estimates on this manifold, so they modify the arithmetic via the Ricci flow. So they run the Ricci flow for a very short time to get good estimates on the matrix and on the distance functions. And then with this better estimate, they could go to the limit with a kind of diagonal argument and show that the limit space is still homomorphic to a three-dimensional manifold. So the limit is going to be a topological manifold. Okay. Now, since this space over RP2 is three-dimensional, if it is a limit of three-dimensional manifold, it must be non-collapsed. So by this result of Simon and Simon Topping, it will need to be a topological manifold. But at the tip, it is not topological manifold, and so it cannot be a Ricci limit. Okay, so you have this strict inclusion of RCD with the Riemannian, with the Ricci limit. However, I don't see it as a so I see this as a kind of fact, which is both positive and negative side. So the positive side is that you have a larger class of spaces where you can prove a lot of theorems, which hold in a more general setting than Ricci limits. The negative side is if you would like to have a syntheticalization of Ricci limits, then this is still a bit too large setting. But say from point of view of application and from a point of view of the theory, I think that it is just good if you have a good, say, synthetic framework where you can prove as much as you like, and then apply this in the smaller setting if you wish to. Okay, so this is about these implications, these inclusions. Now let's see some examples of RCD K spaces and RC star K spaces. Actually, all the examples that I'm going to discuss here are both RCD and RC star. So we have just seen that Ricci limits, no matter if collapsed or not, are RCD K spaces. Then five-dimensional Alexander spaces with curvature bounded from below, they are RCD-Kn. So you have to be with the usual interplay between sectional and Ricci curvature. So if you, in the smooth setting, if the sectional curvature is bounded below by 1, then the Ricci is bounded below by n-1, and the same is true here. So if you have an n-dimensional Alexander space with the curvature bounded below by 1, it will be an RCD n-1 n metric measure space. And which measure I'm thinking here, because Alexander spaces are metric spaces, while RC spaces are metric measure spaces. So you have to fix also a reference measure. And here the natural choice is to choose the Hausdorff measure of the relevant dimension. Okay, and this fact that Alexander spaces coincide, Alexander spaces are included in RCD is actually not trivial, and the fact that the Cheeger range is quadratic is a result of deep works by Perelman and Oshioya, and the fact that the CD condition is satisfied was proved by Petroni. Okay, and okay, maybe I just had one more caveat here. So this inclusion is very natural because Alexander spaces are non-smooth spaces with sectional closed bounding from below in a synthetic sense, while RCD are non-smooth spaces with Ricci bound below. So it is natural that the lower bound on the sectional implies a lower bound on the Ricci. Sorry?
There's a question.
Two questions.
Okay. Yeah. Let's see. Ooh. Yeah. Are there more issues by considering XD branching spaces? There are a lot more issues, but it depends to what. So, Diak Fren Anshen, say to which statement you are referring to. So I think let's say some statements very much rely on the non-branching. So just saying, are there more issues by considering XD branching? The answer is yes, but in some cases you can still work. A good balance between, say, wild branching and non-branching is what is called essentially non-branching, which means that when you take two probability measures, which are absolutely continuous, and then you consider the geodesics which are performing the optimal transport, then you ask that say almost all the geodesics are non-branching. If you assume that, you're basically saying that optimal transport, even if your space may have some branching geodesic, your optimal transport basically doesn't see them, and so you can work with the good geodesics. But in general, having branching geodesics is making your life much harder. So Daniele Di Donato asks, what is the inclusion for CD spaces? The inclusion you mean in the previous thing for this? So for this, you have, again, okay, so the first one is strict as well. So you have that CDK infinity includes strictly C star Kn, and you have exactly the same example. So the Gaussian space is CDK infinity, but is not C star Kn for any n. So exactly the same. Regarding inclusion of CD star Kn and CDKn, I will, if I have time, and I don't think so. So I tell it now. The work of Cavalletti and Millman is actually more generally for CD star. So what they prove is that in case you are of finite measure and your space is essentially non-branching, so it is a key assumption, essentially non-branching, then the CD star condition is equivalent to CDKn. So CD star is equivalent to CDKn if you assume the space to be essentially non-branching, and it is proved for finite measure. We expect it to be true also for infinite measure, but the proof for a moment is not there. And what about limits? Well, CD star, so this contains the Ricci limits because, for instance, strictly, because C star contains physical structures which are not Ricci limits, and so the inclusion is strict also there. I think I answered. Okay, good. Okay, so this was about, so I was talking about the Alexandrov spaces. Okay. Now, if instead you are interested in weighted smooth Riemannian manifold, then they fit very well in the RCD-KM framework. Indeed, consider a smooth Riemannian manifold, Mn, with a method G, and consider the weighted measure. So you are considering the measure M to be the volume measure multiplied by a smooth weight, a smooth function psi, okay? And you get this reference measure M, which is a multiple by a function of your volume measure. Then in this framework, so this framework was very much studied by Bakri, Emri, Ledoux, etc. They proved fantastic theorems in this framework, and they detected a the right way of understanding Ricci curvature is to say perturb the Ricci tensor of your metric G with this kind of Hessian of the weight psi normalized in this way. So you are considering, okay. And they observed that, I will say more details later. And then they observed that from the point of view of Ricci curvature, from the point of view of functional inequalities, adding such a weight, so multiplying your volume by such a weight, is actually changing the behavior of your space from the point of view of dimensions in functional inequalities. So when you have this weight, your space behaves from the point of view of functional inequalities as a manifold with different dimension. Okay, and so they introduced this what is called now Bakry-Emery Ricci tensor, which also has a parameter n playing the role of upper bound on the dimension. And so now to go into the real math. So we say that your weighted manifold has n Ricci tensor bounded below by k if this guy, which is by definition the n Ricci tensor, okay, which depends on the metric G, on the weight psi, and on this parameter n, which is the Ricci tensor of your Riemann metric, you subtract the difference between your parameter big N and the dimension, the topological dimension of your manifold, small n, and you multiply it by the Hessian of your weight psi to power 1 over big N minus small n, normalized by psi 1 over n, big N over small n, and you ask this, which is a quadratic form, to be bigger or equal than kg. Okay, and this is the notion of n Bakry-Emery Ricci tensor bounded below by k, which is very much studied. Now, it turns out, it was proved by Sturm, that such a condition, so n Bakry-Emery Ricci tensor bounded below by k, is equivalent to say that the associated metric measure space is an RCD Kn space. So it is going to say that the manifold with the Riemannian distance function and with this weighted measure is RCD Kn. And this idea, so this fact that even if you have a small n dimensional manifold, when you multiply the measure by a weight, you are increasing its synthetic dimension. It will be very useful also in the final talk when we are going to see the localization technique, and we are going to see that and this fact that a one-dimensional object, say an interval endowed with a shootable measure, behaves like an n-dimensional space, is going to be very useful there. Okay, so this was about weighted measures. Then I already used it in the previous slide. So when you consider cones or spherical suspensions over RCD n-1 n spaces, these are RCD 0 n spaces. This was proved by Ketterer. 0 n plus 1 spaces. This was proved by Ketterer. Then the RCD condition is stable under taking quotients, orbifold, metric measure variations of manifold with Ricci curvature bounding from below. And this was joint work with Galat Garcia, Kell, and Thosa. And then another natural class of spaces which enter into the RCD Kn framework is the one of stratified spaces with Ricci curvature bounding from below and cone angle less than 2 pi. And this is a recent work by Bertrand, Ketterer, Mondello, and Richard. I see a question in the chat. No. Okay, so these are a list of, so a non-exhaustive list of examples, but which permit us to make some moral from these examples. So the moral that I would like to draw from these examples is that in doing Riemann geometry, one naturally encounters non-smooth spaces. For instance, when one takes limits of Riemannian manifolds, which is a procedure which is used very, very often in contemporary differential geometry. For instance, if you are doing some contradiction argument, you want to prove that some inequality is satisfied among spaces of lower bound on the Ricci. What you do is assume a contradiction that it is not the case, then apply Gromov compactness, you pass the limit, and if in the limit you are able to get a contradiction, then you prove that your inequality holds. Taking limits is also very much used in blow-up arguments, typically when one runs into singularities. Geometric flows typically develop singularities. This is you are seeing this in these beautiful lectures also by Bamler in this week. So taking limits and singularities in Riemannian manifold, this is something that is often unavoidable in current research. Another procedure that produces singularities is when you take quotients, cones, or foliations of Riemannian manifold. For instance, you start from a smooth manifold. This smooth manifold has some symmetry. In order to study the space, you take the quotient. But if these symmetries are not do not act properly and discontinuously, then the quotient will have some and freely the quotient will have some singularity. And then you want to say something. You want to study the spaces. So the message of these examples is that if the smooth spaces you started with have Ricci curve running from below, then the non-smooth spaces that are arising as limits, as quotients, as foliations are RCD. Okay, so you can apply all the results that have been produced in the last 10 years in the RCD setting, and there is quite a bit of structure, quite a bit of inequality. So basically, maybe all is a bit too much, but say almost all of the classical comparison inequalities, both geometric and functional, are now in the RCD setting, and the structure theory of RCD, we're going to see it tomorrow, is covers at least the Cheeger-Colding papers, and it covers also Colding number paper of the constancy of the dimension, and a bit of the last paper of Cheeger-Colding number, but there is more work to be done. So at least so. But what I'm saying is that say the structure of RCD is very much advanced, and so you can apply all of this machinery in this setting of limits, of quotients, cones, foliation, etc. So the message is that RCD-K spaces can be seen as an extension of the class of smooth Riemannian manifolds with Ricci bounded below by K and dimension bounded above by N, which is closed under many natural geometric and analytic operations that we encounter almost every day in doing modern different geometry, and so it can be useful also for a person who is interested in smooth spaces but encounters these singularities just working with them. And in lecture 4, we're going to see some application of this kind. Okay, now I have 5 minutes, so I think I prepared for another hour, so I will just squeeze what I want to say. So what I wanted to cover is the Bochner inequality, because then tomorrow I would like to cover the structure theory, and in the last lecture I would like to cover localization technique. So Bochner inequality, I will just give the statement and I will have no time for discussing the proof. So we say that a metric measure space has the so-called Sobolev-Lipschitz property, STL, if for every Sobolev function in W12 with weak upper gradient in L2, with weak upper gradient square less or equal than 1, pointwise almost everywhere, such a function is a Lipschitz representative. So this is kind of natural from, say, in the smooth setting, because if a function has a gradient less or equal than 1, you just integrate the gradient along curves, and you get that the function is you integrate the gradient along geodesics, and you get that the functional is the function is 1 Lipschitz. If you are in a metric measure space, this is a requirement, kind of, it is a regularity requirement on the space X, because, for instance, if the space X has not enough curves, then you cannot integrate this inequality, and you cannot get this information. So you can think of this sober fluidity property as a regularity on the space X, having enough rectifiable curves. Okay, so Ambrosio-Gigli and Savarè, in their Duke paper, proved that the RCD K-infinity condition implies this sober fluidity property. So it is a kind of a natural assumption in the RCD Kn set, in the RCD K-infinity setting. So we say that a metric measure space satisfies the dimensional Bochner inequality, let me call it BI, Bochner inequality with parameter k and n, k lower bound on the Ricci and n upper bound on the dimension, if the space is infinitesimally Hilbertian and sober fluidity property holds, and this kind of weak version integrated by parts, this weak version obtained integrating by parts of the Bochner inequality holds. So here I'm saying that I take a function in W12 with Laplacian in L2, because I will need to take the Laplacian and I will need to take the divergence of the gradient. And for any test function which is Lipschitz and with Laplacian in L infinity, the following holds. So this is nothing but writing down the Bochner inequality on F, multiplying it by a test function psi and integrating by parts. Okay, so this is the definition of Bochner inequality in a metric measure setting. Okay, now the question is: are RC star Kn and Bochner inequality equivalent? The motivation, of course, comes from the smooth setting, where the Bochner identity is a really fundamental tool. So the Bochner identity in a smooth Riemannian manifold, write down as this formula. You've seen it in the last week in the Thomas Richard course in Riemannian geometry. And of course, if the dimension of the manifold is bounded above by n and the Ricci is bounded below by k, then this identity translates into a very powerful inequality. So here we are just replacing Ricci grad f, we bound it from below with k times grad f squared, and we just use the Cauchy-Schwarz inequality for symmetric matrices to say that the norm of the Hessian squared is bounded from below by 1 over n, which is the size of the matrix, times the trace squared of the matrix, which is the Laplacian of f squared. Okay, and now once you have this classical dimensional Bochner inequality, you just multiply this by test function psi, and then you integrate by parts, and you get the previous formula. So this formula here. Okay, and let me just mention that this Bochner inequality is a very fundamental tool in smooth differential geometry of manifold with lower bound on the Ricci. For instance, it is a key tool in proving the splitting theorem of Cheeger-Gromov. It is very useful. So once you have it, the Lichner-Horowitz bound on the spectral gap is just one line proof, and it is also very useful to prove an upper bound on the first Betti number. This was done by Bochner using Hodge theory. So it is a very powerful tool. Here I just mentioned 3 applications that I like, but there are many more. Okay, so now what is the relation with the RCD? So actually it was proved in 2 independent papers, one by Erbach and Sturm, and the subsequent and independent one by Ambrosio, myself, and Savarè, that the Bochner inequality is equivalent to the RC star Kn condition. So a measure space satisfies the dimensional Bochner inequality if and only if it is an RCD star Kn space. I mentioned that this result is bridging two formulations of Ricci curvature which are very different in spirit. So the approach via Bochner inequality is a kind of Eulerian formulation of Ricci bounds, because while the optimal transfer point of view, the RCD approach, which is convexity along geodesics, is kind of a Lagrangian formulation of the Ricci. So if you know a bit of fluid dynamics, what do I mean with the Eulerian formulation? So Eulerian means that you are taking a picture of your fluid at a given time, and you see at a given time the velocities at every point. While the Lagrangian formulation, you are following every particle of your fluid. Instead of taking the picture of all the fluid, you follow each single particle along. And the Lagrange, so the RCD responds to the Lagrangian because you are taking the convexity along geodesics, so you are really following in time what happens. While the Bochner inequality is taking a picture of your space, and your camera is given by this test function, which are testing the Ricci curvature at different points. Okay, and the two proofs by Herbert and Sturm and the Bonn team and the Italian team were quite different. So the approach by Herbert and Sturm is based on equivalence between an entropic curvature condition, which involves the Boltzmann entropy, and uses weighted heat flow. So it is using very much weighted linear flows, while the approach of the Italian team is say more nonlinear in nature, because it is using nonlinear diffusion equations in metric spaces, and more precisely, it is using the porous media equation, which is the nonlinear gradient flow of the Riemannian entropy as a bridge between the Bochner inequality and the RCD star Kn condition. And you also mentioned that in case n equal to infinity, the equivalence between Bochner inequality with n equal to infinity and the RCD K infinity was already established by Ambrosio-Gigli and Savarè, and the proof is much easier because you can work directly with the heat flow. Okay, can I have just 1 minute just to say what is the main idea?
Yes. Okay.
Okay, I will be very quick. Sorry, I will sketch all the details. I will just forget all these. Just let me mention what is some key ideas in our approach to prove this equivalence. So the key idea is to use gradient flows as a bridge between the Eulerian point of view and the Lagrangian point of view. So we have seen before these AVI flows. So here we can use the same. So here the idea is to prove that we have a well-defined EVI flow. Remember here the notion of EVI, but now of the n-dimensional Riemannian entropy. And the proof is made in two steps. One step is proving that the RCD star is equivalent to say that the Riemannian entropy admits an EVI 0 gradient flow in case of K equal to 0. And the other half of the proof is proving that the Bochner inequality is equivalent to having EVI flow for the Riemannian entropy. Okay, so you are using this gradient flow as a bridge. So here you have RCD, and here you have the Bochner inequality, and then in the middle, for bridging the two, you have the EVI property for the Riemannian entropy. And what is the candidate for being the EVI flow for the Riemannian entropy is the porous media flow, which is defined by this nonlinear parabolic PD. And I think that I'm already over time, and now the details will start. So I think it's a good moment to stop. And tomorrow we're going to see structure of RC spaces, and in the final lecture we're going to see isoperimetric inequalities and sharp geometric and functional inequalities in synthetic spaces with application to smooth manifolds. Okay, thank you very much for your attention.
Thanks. So, is there a question?
May I have a question?
Yeah.
So it's a rather vague question, but to what extent the fact that the Cheeger energy is precisely quadratic and not that the norm induced is, let's say, isomorphic to a Hilbertian norm, to what extent it is important?
So this fact is true. So the fact that it's so if you have, I don't understand the question. So the question is that is this so is the question why this is true, or the question?
No. The question is, so the assumption is that the Cheeger energy is quadratic.
That's correct.
Now my question is, if we relax the assumption and only assume that the Cheeger energy induces a norm which is isomorphic to a Hilbertian norm.
The Cheeger energy induces something which is isometric to an Hilbertian norm. I think these two conditions are equivalent, because I think that is a kind of
the fact that Cheeger energy is Hilbertian norm, it's equivalent to parallelogram identity.
Yes.
And that it is isomorphic to Hilbertian norm is equivalent for the space to have type 2 and cotype 2. So it's a theorem of Kvapping.
Okay, functionalized. Okay, so this is something of this is kind of general results of Banach and Hilbert spaces. You're thinking. Yeah, got it. Yeah, it should be interesting. Let's see. Let me say that, say, in computations. So let me give you one abstract answer and one practical answer. The abstract answer is that it could be interesting to understanding it, and in particular, say, how more general would be this kind of just assuming that it is isomorphic to its Hilbertian norm. So how more general this is, and for instance, say, if you put a sanity check would be to start with some LP norm with P, say, between 1 and infinity, and see what happens there. Probably it is not true that it is isomorphic to an Hilbertian norm, but you are more expert than me in that.
No, it's not true.
It's not true, right? So it would be interesting to see, say, how more general it is. So which spaces you are considering in addition. And this is the abstract answer. The practical answer is that, say, in day-to-day life, when you want to prove theorems in RCD, what you do is you integrate by parts, and it is really useful to have that the Cheeger energy satisfies, so is a Abelian form to say that it is really induced by a scalar product, so that you can really have a scalar product of grad f, grad g, and you can integrate by parts, and you can get the Laplacian is linear, and so on. So from a practical point of view, I think it is quite important to have that it is really quadratic, but I think it is also interesting as an abstract question what you're asking.
Thank you.
And also a question in the chat.
Yeah. See? No, my computer got frozen. I don't know why the chat disappeared from my computer. I cannot see it. If someone has some question in it could speak, could please speak it. Okay, now got it. Thank you for the lecture. Okay, Cristiano Sormani introduced. Okay, got it. Cristiano Sormani introduced us to many different notions of convergence of metric spaces. Yes. Could we expect to find a right notion of convergence such that the corresponding closures of the class of manifolds with bound Ricci dimension is exactly one of these spaces that we are defining here, say RCD? Maybe, but maybe not. So I don't
doubt it.
Yeah, I doubt it. I doubt it. I think that this and yeah,
it's kind of a larger class.
Yeah,
it's a larger class of spaces. So the same thing happens with the limits that I'm going to be speaking about. The class of limits that we actually reach is not as large as the class we've created.
Yeah, I agree. So I think say this example of the cone over RP2. So this is just one example, but I think that one can build many more. And I think that the point that this is a large. So I think that the point is that so this is a priori a larger class. It is interesting because you can prove several theorems there. You can prove basically almost all the theorems for Ricci limits now are also in the framework of RCD. So I think in general, so it is an interesting question a priori, what is the relation between Ricci limits and RCD? But say, if you are more pragmatic, say, how can you use this theory for the other one? You can say, do it without knowing, right? So is one reason that this class is also closed with respect to many other operations. Exactly. So the point, so I think that's one of the strengths of this RCD theory is that it is closed under limits. It is closed under splitting. So for instance, if you know, so for instance, one thing that I think is not clear for Ricci limits is that if you, what is that? So is that if you have a Ricci limit space, then you have the splitting theorem. This was done by Cheeger and Colding, but as far as I know, it's not clear if the other factor is also a Ricci limit. So the fact that you are splitting isometrically an R factor, but it's not clear if the other factor is a Ricci limit itself. And this is while in the RCD KN setting, one proves that if you have an RCD 0 in space which contains a line, then it splits, and the other factor is RCD 0 n minus 1, and so you can do everything that you want on the other factor. And then also say for quotients, foliations. If you want to work only with the Ricci limits, sometimes it is a bit tricky to say that the quotient of Ricci limits is Ricci limit itself, etc. So I mean, say there are two different approaches. Each one has its own strength. So Ricci limits are super strong for proving structured theorems. The RCD have the advantage of being synthetic and of providing a framework which is closed under many natural operations that maybe you would like to do. Cristiano, do you have something to add? You are no,
I think that's good. Sorry.
Good.
I'm still working on adding slides to my lecture so I don't go short.
You are busy. You are busy.
I'm sorry. But yes, I think that's the main point.
Right.
I mean, I remember when it was just plain CDNK spaces, everyone would say, oh, is that all the limit spaces? And people were like, no, because the limit spaces would split, and they don't. Mm-hmm. So,
Okay, thank you, Andrea. Thank you very much for this lecture.
Thank you.
So maybe we stop here and see each other tomorrow. Well, Christina will give the lecture in the beginning of afternoon for us. Okay, so see you then.
Okay, see you.
Merci.
Bye.
All right. Bye.